Our Lesson 50 homework is to create a Deluxo tilt meter by updating our Lesson 45-46 Tiltomatic code with what we recently learned about gyro data, complementary filters, and steady-state error reduction. I won't be repeating the explanation of the Tiltomatic code. If you haven't seen the Lesson 45-46 homework yet, there's a link in the description below this video. For that matter, I won't be explaining the complementary filter or steady-state error reduction either, just showing how it's integrated into the Tiltomatic code. Watch Paul's Lesson 48, 49, and 50, or my Lesson 48, 49 homework to catch up on that. There are links to both in the description below this video. In the Lesson 45-46 homework, we draw the bubble 1 pixel at a time in every cycle of the while true loop. This slows the while true loop considerably. Loop duration was shown to be consistently in the 0.1 second range. In this homework, we'll be blitting an image of a bubble onto the OLED instead of drawing it over and over. If you're unfamiliar with blitting, you might want to watch 10 minutes or less about SSD 1306 graphics and animation. There's a link below. The process is pretty simple. You create an image of the bubble as shown on the right. This image is only 9 bits wide and 9 bits high, so the bubble can only be roughly circular. Save the image as a monochrome 1 bit per pixel portable bitmap file. Copy that file to the Pico root folder. Read the image into a MicroPython variable and blit the image onto the OLED rather than repeatedly drawing it from scratch. With this approach, loop duration drops into the 0.04 seconds range. That's a 2.5 times improvement in loop speed compared to the redrawing approach. If it isn't too fast, that should make the program more accurate and responsive. Let's have a look at the new parts of the code. We start with the usual imports, but we also import frame buff because we're going to be blitting the image of the bubble onto the OLED. The remainder of this section is the same as the Lesson 45-46 homework. We configure the OLED and the IMU, and we set some initial values. As in Lesson 45-46, we define variables that specify the screen boundaries for the bubble and the axes, and calculate slope and y-intercept values that will scale the movement of the bubble to represent pitch and roll. Here we read the bubble.pbm file. We discard the image type variable, but use the width, height, and data variables to load the image into the frame variable. We've added gyro data to our calculations in this lesson, so we have to input gyro x and gyro y from the IMU. The gyro and accelerometer data pass through a complementary filter. The complementary filter output is adjusted to remove steady-state error. Next, we calculate pitch adjust and repeat these calculations for the roll parameters. Once we know pitch comp and roll comp, we calculate Cx and Cy, the center coordinates of the bubble. Note the correction for image height and width. This is because blit images are located by their upper left corner, not their center. Finally, we clear the OLED display and display pitch and roll as text. We blit the bubble image onto the OLED in line 109, replacing the previous logic shown below, which actually drew the bubble. This approach reduces loop duration from the range of 0.1 seconds to 0.04 seconds. We draw the horizontal and vertical axes, show the results, and repeat the loop. And here's how it looks. Here you can see the system is fairly responsive and immune to vibration. The bubble looks relatively circular too, although you don't want to look at it too closely. The depth of focus of my camera isn't quite up to the job, but I'm sure you get the picture. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.